What is entropy, really? It's a fundamental quantity that is used heavily in the context of thermodynamics, and yet it's not something that we can get an intuitive grasp on, unlike temperature, heat, or work. It's a quantity that we seldom think of as more than a number to find on our tables and plug into our thermodynamic equations. Because it's a difficult concept to grasp, there is a common misconception that is made about entropy, which is entropy as disorder, or a measure of disorder or chaos. This is the intuition that you may already have, as entropy is consistently taught with this idea. But this is an oversimplification, and in many contexts, just wrong. Disorder can certainly be related to entropy, but it does not define it. The issue with this incomplete intuition is that it becomes difficult to understand and apply entropy to various contexts. For example, say we have one system with a volume of 1 liter with 4 particles and expands into a vacuum to occupy 2 liters, but remains at the same temperature. What is the change in entropy? If we keep our notion of entropy as disorder, this question becomes difficult to answer. What exactly is disorder in this case? And so, seeing the issues of this, we want to clarify and ground our intuitions of entropy properly, and show that a different sense of entropy is more useful in understanding entropy and applying it to a variety of contexts. First, we will look at how the concept of entropy was derived via the Clausius equation. Then we will look at a different take on entropy via the Boltzmann equation, which gives us a better sense of what entropy really is. To show how the two seemingly different takes of entropy relate, we provide a demonstration. Lastly, we give a couple of examples of how entropy is used outside the thermodynamic context.
In 1865, Clausius published a paper called On the Various Forms of the Laws of Thermodynamics that are Convenient for Applications. In this paper, he defined entropy as the ratio of heat to temperature. Let's derive this definition. Experimentally, Clausius observed that for reversible heat engines, the ratio of heat input to rejected heat is always equal to the absolute temperatures of the high and low reservoir. For irreversible processes, this relation does not hold. Combining equations 1 and 2 for a single heat input and heat output gives us this equation. For any number of heat transfer terms, this equation becomes. This equation is known as the Clausius inequality. The Clausius inequality for reversible cycles becomes, simplifying it further, we get the Clausius definition of entropy.
In this video, we're going to discuss the Boltzmann definition of entropy, which states that for ideal gases, entropy, or S, is Kb times the natural log of W, where Kb is the Boltzmann constant and W is the number of different arrangements the gas can occupy. So, how do you calculate W? Let's consider a case where we put ideal gas particles in one of two states, left or right. With n equals 4 particles, there are a total of 2 to the n ways these particles can be arranged. Now, of these ways, how many have an nl number of particles on the left, and an nr equals n minus nl number of particles on the right? This is given by the binomial coefficient, which says that w, which is a function of the number of particles on the left and the total number of particles, is n factorial over nl factorial times nr factorial. Now that we know how to calculate W, let's consider the case when NL doesn't equal NR. We'll have 3 particles on the left this time and 1 in the right. We can see that this case results in greater entropy because it decreases the denominator of W. But if NL equals NR, like in our first case, then we can say that the system has achieved equilibrium, or that W equals W max. The new formula for W then becomes n factorial over n over 2 factorial squared. With this in mind, let's calculate the entropy of our first case. which is equal to a kb times the natural log of W max. Substituting the formula for W max gives us the following, and if we plug in the value of n and the Boltzmann's constant, we get that the entropy is equal to 2.47 times 10 to the minus 23 joules per Kelvin.
Okay, so from the Clausius definition, we know that the change in entropy is directly proportional to the ln of the final temperature over the initial temperature. So as temperature increases, we would also expect entropy to increase. Yes, we have two different colored balls, some that are blue, some that are silver, arranged in two blocks of 8 to represent the system at initial temperature. And to simulate an increase in temperature, we would find a vibration with the Pasco Scientific Materials mechanical wave driver driven by a function generator. The way this works is because the average velocity squared is directly proportional to temperature, and we know that the average velocity is equal to distance over time, which is also the same thing as distance times frequency. And so the frequency is also directly proportional to temperature. So as frequency increases, we would also expect temperature to increase. In the initial system, we are calculating entropy using Boltzmann's law, and to do this, we had to calculate the maximum number of states that this can exist in, and so we used combinations. And so starting off with that first row, you have 8 blue balls and you choose 4 of them. So then there are 4 remaining, you choose the remaining 4. And then the same thing for the silver balls. And from that, we calculated the initial entropy. So the first frequency we applied was 50 hertz, and we can show that happening here. And so then again, we calculated entropy using the same process, same equation. And then for the second run, we applied a frequency of 100 hertz. And then again, calculated entropy using Boltzmann's law. And then finally, we applied a frequency of 150 hertz. And finally, again, we calculated the entropy. We started off in an initial state and increased the frequencies to represent an increase in temperature. And with each increase of frequency, we also noticed an increase in entropy. So this confirms that as temperature increases, so does entropy.
Now let's talk about the connection between entropy and the Big Bang. Recall that last time we calculated the entropy for ideal gas particles that were either in a left or right state using the Boltzmann definition for entropy. We can extrapolate this concept to talk about the universe as a whole, which we'll represent with 4 macrostates. Each macrostate contains a certain number of particles whose states are represented by their position and momenta, and these particles are getting closer and closer together, showing that entropy is decreasing over time. The particles update their microstates or position and momenta after every tick of time to make a new macrostate. But different microstates can lead to the same macrostate, and this clears up a common misconception, the one that entropy increases due to disorder. Entropy increases due to the randomization of microstates over time, so an increase in disorder does not necessarily mean an increase in entropy. And now that we've cleared that up, let's come back to our model universe, consisting of 4 macrostates with particles coming closer and closer together, showing that the entropy is decreasing over time. Larger dips in entropy due to particles increasingly sharing similar states over time are less probable to happen. But if you wait for an infinite amount of time, all possible arrangements of particles will occur, including the most improbable one, the one in which all particles end up at the same place at the same exact time. And such an arrangement would give you the Big Bang. By looking at radiation left over from the Big Bang, scientists have calculated that the entropy of the universe at the time of the Big Bang was about 10 to the 88 Boltzmann constants, and now it's about a quadrillion times larger, primarily because of black holes and the sheer amount of particles that they make up. And because entropy has always increased since the time of the Big Bang at macroscopic scales, it's often interpreted as the arrow of time.
Let's look at how entropy is used in chemistry or physics. First, let's look at the units of entropy. It is energy over a unit of temperature. What does that mean? It means that something with more entropy can hold more energy without increasing the temperature. In the demonstration, we showed how the increase in temperature changes entropy, but what if temperature remains constant? This is where microstates or multiplicities can help with our understanding. Compare molecule A with molecule B, or atom A with atom B. Which has, or the potential for, more entropy? The answer is molecule B and atom B. Why is this? It's because they can be found in more different arrangements or microstates than A. In the case of molecules, B has more degrees of freedom or ways it can store internal energy, either in the form of rotational motion or vibrational motion, before it is transferred to translational motion. Because temperature is proportional to kinetic energy, we can see how energy can increase in the molecule without increasing the temperature. This is directly related to a molecule's microstates, and so B can have more entropy. It is a similar case with atoms. Some atoms have more energy levels that its electrons can occupy. It takes more energy to occupy higher levels, so an atom that has more states for electrons to occupy can have more entropy.